Okay, we're gonna go back a little bit to the calculation of bending moment and the shear force. This time, however, we will not go back to drawing the graph. We will talk about calculating at a point again. This time we will not rely on the equilibrium. We use the technique we learned it also in the first half, which is called the virtual work. Since we already learned about the theory, today there will be no hardcore proving at all. We just revise a little bit on what we know about it, and we're gonna apply on it. Okay, we'll talk about the work and the virtual work that was addressed in lecture 11. We also will talk about the connections, because it will be relevant to the calculation. This one here we'll talk about two connections in particular that is actually also addressed in lecture 10, just in case of revision. And then we'll see how we apply the knowledge we already have, or I hope we do have, to solve the new thing. Not the reactions anymore. This time we'll solve for bending moment and shear force at any given point in the structure. Okay. Now let's talk about the force, the work done by the force first. Okay. Again, we discussed about the force time distance. However, it has to be with the cosine theta. Actually, per se, it will be the force time the distance on the same direction, on the same line. Okay? If it's going together, then the work done is positive. If it go against each other, work done is negative. Okay? Then we go to the proof for the moment, the work done by the moment. Relying on the work done. Again, I'm not going into detail. I'm just remind you what we have done in the first half. Then using the concept of the work done by force, we extend that idea to prove the work done by the moment. And we work out that the work done by the moment is the moment itself times the angle it rotates. The same idea with the force. If the moment and the rotation going in the same direction, the work done is positive. If it go against each other, the work done is negative. Okay? In this picture, because the moment and the rotation of the body is in the same way, in this case clockwise, both are clockwise. Therefore, it is positive work done. We expand that even further to see how we calculate the work done by distributed load. We only cover the uniformly distributed load, meaning it's all the same throughout the distribution, meaning the magnitude of this force is always W, okay, force per length. And we work out that it's actually equal to that magnitude times the area under the spread shape. If you want to use any other equation, prove it. If you use W times half this height, only this height, average of these two, then prove it. Do not guess it. If you want to use that, then prove it. Otherwise, stay with this equation. The work done equal to the magnitude of W times the area under the display shape. Okay. Now, this is all three forces, all three work done that we can calculate since the first half. As I said, it's just revision here. So one of the key calculation of the virtual work is that you must see those unknowns. In this case, internal forces. One of the steps is we have to release constraint, which then the two will be involved in this case. Right? We release constraint. At the time we change the condition of the support so that we can see reactions. Okay? Then the second step, we add in the reaction back to the system, but in this case we want to calculate, we want to see internal forces. We will change something else, not the support. Then we will have to add in the missing force. In this case, the relevant internal force. In one case will be bending moment, in the other will be the shear force. We are not talking about axial here. Okay? Then it becomes equivalent again. Then we start to move the structure a little bit, or in this case displace it. in the way that those internal forces work. So it appears in the work done calculation, equation. Okay? However, this movement is not real. Okay? It's just imaginary. And then we apply the equation we already proved again, that the work done of all forces and moment acting in an equilibrium system will be equal to 0. Okay? The tool that we need to use, that one there, will be releasing the constraint of the bending moment at the usual place when there is no connection, just a piece of material. It resists shear force, it resists axial force, it resists bending moment. At this pin joint, it only resists shear force and axial force. It doesn't resist moment. So the pin joint is the one that releases the constraint in terms of bending moment. Okay? The second one we're talking about is the slide, the fixed slide. Okay? Because it releases one force. So if we set up that slide, that line, to be 90 degrees to the member, it will release the shear. Okay? So that's the one we're talking about. Basically, it will leave the axial force and bending moment inside the material. Questions, or should I move on? Okay, that's it. That's theory. We have already learned it. We have already done it. Okay? Now, this is one of the most simple one. Okay? Just simple support beam, one load. What I want to find is the value of bending moment at point B and the value of shear force at point C. If you remember the first half, the strength of the virtual work is that you don't need to calculate anything else. You can calculate the value you want to know immediately. This will be the same case here. Meaning we don't need any reaction at all. We can go straight to bending moment equation and shear force equation and calculating the shear force. Okay? Let's trace the step. The first step said release constraint. Let's say we're going to calculate bending moment at point B first. The first step, we release the constraint at point B in such a way that it doesn't resist bending moment anymore. The only way we can change the condition is that from normal material, it becomes the pin joint here. Meaning now, at this point, joint B, at point B, it resists axial force. You cannot pull it apart. You cannot slide it up down. Meaning it resists shear, but you can rotate it around point B, so it doesn't resist moment. Okay? So that is the first step of releasing the constraint. The second step is that we have to apply back the bending moment, apply back the relevant internal forces. Don't forget, when we talk about internal force, we are not talking about one force. Internal force is always a pair, equal and opposite at one point. Therefore, in this case, we have to add in the whole pair, that one and that one. Now, how do we say that is smiling or sad face? Okay, it comes from that one. That one is smiling, right? Correct? Now, this one here, before I start, I already decided that I will assume smiling positive. Okay? So this is the symbol I will use. On this side, on AB side, the moment acting at point B will be that one. Correct? Right? Therefore, that one apply onto the AB side. On this BD side, the one that acting on point B is that one. Correct? Therefore, we apply that one onto that one. Okay? Next, it is the same step as we done before. Next, we start displace it in such a way that these two bending, or at least one of them, do the work. How does moment do a work? It has to rotate, correct? So the idea is that I will try to rotate either AB or BD. But because the system, if I rotate AB, point B move up, for example, rotate AB anti-clockwise, then point B move up. If point B move up, point D cannot go up. Point D has to stay with the support. Then BD rotate at the same time anyway. Okay? So once I do it, it will be in this one. But this one, I rotate it back down. Okay, meaning I rotate AB clockwise, meaning point B will come down. Okay. Now, the way you name it, it depends on which way you want to name it. This one here, I want to relate everything with delta B. I think it's easier that way. So I will only name delta B for that matter. Okay. Now we're gonna calculate it. We done the first 3 steps, right? Release the constraint, put back in the internal forces, displace it, and now the calculation. Sigma U star equal to 0. Move that one there. There we are. Now there are 2 moments, 1 force in this system. If we notice, they all move, right? Moment rotate. The point load B coming down, correct? So there will be 3 terms in this one here. There we are. That one corresponding to that one. Okay? BM time rotation here. The theta here. However, this theta equal to delta B over 2. Correct? That's the term delta B over 2. Because that one rotate anti-clockwise, but AB rotate clockwise. They are opposite direction. Therefore, that work is a negative work done. We agree? Now, the second one, that term, well, I actually work from left to right basically. That term comes from 100 kilonewton going down. Delta B from here coming down here is also down. Correct? Therefore, the work done positive. The force time this distance, moment time angle. Okay? That moment will time that theta there. However, that theta is equal to delta B divided by 3, that term. Okay? The moment itself going clockwise, BD going anti-clockwise. The work done negative here. There we are. Because the way I set it up, every term have delta B. So I can take delta B outside into that term. Argumentatively, delta B is not 0, small but not 0. Therefore, inside here must be 0. There we are. Only one unknown here. And therefore, we can calculate bending moment straight away. If we trace the calculation, we should find that this bending moment is positive. What does positive mean? We assume the correct direction. Like you said assume, you said smiling. Both correct. We assume smiling. Therefore, this one here is smiling as we assume. This is the strong point for bending for virtual work. You can always calculate the value you want, relying on nothing. Go straight to it. The weak point is that every single calculation has to start from 0. Okay? So let's go back and find out the shear, the VC. Shear force at point C. Well, the question asks bending moment at point B and shear force at point C. They ask for on different point. Again, we start from 0 again, meaning we start off with the whole beam, the usual beam, right? With 1 point load. Then the first step is we release the constraint. Again, to release shear, that slide doesn't resist force in this direction, right? It resists axial force, it resists rotation, okay? But it doesn't resist sliding. Therefore, in this case, it does not resist shear. So we release it already. Then once we release it, the usual concept is we put them back in. The same explanation. If I assume this box, that one corresponding to AC, that one corresponding at point C from C to D. Okay, the same free body have been always drawn. Is that confused or not? I can explain in other words. Now the first step, this one here is a bit confusing, so let me explain slowly. Notice that because it said that the slide doesn't allow the two parts of the body to rotate, but it can rotate together. Meaning, once you slide this up and down, it doesn't slide just up down, it slides as a circle, so that it maintains the angle. That one and that one will be still the same angle, correct? So basically it has to rotate, both has to rotate that way and keep it parallel. Okay, that is the condition of the connection. Now, this drawing is really difficult. However, notice that the shear force, that side, will walk in a circle up to here. The distance it moves is also equal to theta times the radius. Okay? And they said just to make it easier to draw, I have to emphasize this word, just to make it easier to draw, they said rather than draw it as a circle, let's assume that we can draw it just up and down, because the calculation doesn't change. Simplify into that picture instead. However, the rule has to be strict that once you rotate it, that and that still has to be parallel. Meaning that angle and that angle has to be the same angle. Correct? Okay? So now that force will move from here to here. That distance is still theta times 3 meters, the same distance in terms of calculation. Okay? So we're gonna simplify the drawing, but we have to know why and how we can simplify it. That's all. Okay? Now move on. I will get rid of that one then. Leave it the simple one. The word simple is not exactly simple. It's just simpler. Okay? So that's the one. Now notice that there are 3 forces on it, on this body. All 3 forces move, so there will be 3 terms. Okay? Sigma, that one 0. I forgot to change the timing. Okay? That one, don't forget we are talking about forces, we are not talking about moment. The force has a time distance, correct? However, I don't want to have so many unknowns, so I just assign theta. That 100 coming down from here to here, that distance equal to theta times 2, correct? Therefore, the term 2 theta appear here. That V coming from, and it down, displacement down, positive. Okay? Shear, that shear, the left hand side shear, coming down from here to here. The total magnitude is that angle times the distance 3 meters. So 3 theta appear here. The force is down, displacement is down, therefore work done positive. On the right hand side, that one push up, the rotation go up, right? From here to here is equal to that theta times that distance 2 meters. Therefore positive, and then 2 theta here. Okay? Still, force has to time distance, moment time angle. Okay? Then everything has theta star, then you take it out. The same argument, theta star is not 0. Therefore, whatever left inside that bracket must be 0. And it worked out VC equal to minus 40 kilonewton. What does it mean? We assume that one, negative mean is opposite that one, correct? So it becomes that box instead. Simple piece of cake. Oh, come on, from 5 equations you get answer. These are two equations, you get answer. To make it more complex, what? Can it be more complex? Yes, it can always be. There. Let's summarize example 1 first. Okay? The complex case, I will just explain roughly. Details I will ask you to study though. That one. What I want here is I want the shear force and the bending moment at point D. With this system of calculation, you generally need about 8 equations to get to the answers. With full equilibrium, right? Well, with virtual work, one equation per value. Therefore, with virtual work, you need only 2 equations. Let's do bending moment first. Okay, release the constraint, make that again a pin joint. Okay, apply the bending moment back in, and then start moving it. Right? To move it, then I move it this way. Notice that all support condition is satisfied. Satisfied, I would say. That one cannot move, it still doesn't move. That one cannot move, it still doesn't move. That one does not move, it still doesn't move. That is a pin joint in itself, we didn't add it in. Okay? Meaning it can fold. That one is the pin joint that we add in. Okay? Once we move it, then we supply the Bible equation, biblical equation here, right there. Okay, just slow down a little bit because there are so many things involved here. That one comes from the moment. The moment has to time that angle. That angle equal to that height, which we call delta B divided by 2. Okay? Then that one comes from that area, that distributed load. The work done is equal to the magnitude itself, 60, times the area under the display shape. In this part, this is the display shape, triangle. Correct? Therefore, a half times the height times the base. The height is measured from 90 degrees. A half times the height times the base. Okay? So that's cope with that one. Now, notice that force coming down, displacement all come down. Therefore, this part is positive. Okay? Next, that part, the force come down, displacement go up. Triangle but go up. Therefore, this one work is negative. The work is equal to the magnitude itself, 60, times that area, which is again triangle, a half times the 90 degree height times the base. Okay, that is the 90 degree height, this time delta D. Okay, and time the base from here to here, 3.5 meters. Okay, and that bending moment rotate by this amount of angle, which is delta D divided by 2. That bending moment, rotation, that angle, delta D divided by 1.5. Okay, that's it. That's all. Now, even though I have actually designed delta beforehand to reduce the amount of unknown, the one that we have to eliminate. However, in this time, we still have delta B and delta D. So what I have to do is I have to link delta D and delta B boy and delta D dog using similar triangle. That triangle and that triangle. Okay? Therefore, I can work out that delta D is equal to 2 delta B. We agreed? Okay. In that case, I can change delta D into delta B then. There we are. Okay. All terms have delta B. This time, then I'll take delta B out. There we go. Delta B is not 0. Therefore, we work out bending moment. Positive value again. Smiling. Then. As I said, with equilibrium, 7 equations you come to here. Questions? No? So simple, right? Come on, I believe in you. I believe you can do it. Okay? Now, all you have to do is believe that you can do it. That one the same. Go back to the same beam, release shear, then we use that one. Okay? The same one, apply back shear, then move that one down, move that one up. There we are. The rule said this angle, that member and that member has to be still parallel. Therefore, that angle and that angle must be the same angle. Right? And the rest then, because that is another angle here, I will name it theta 1. and we'll name it theta 2. That one and that one the same. Okay, that one is theta 2 as well. The rest then there, and then trace again the force. There we are. That's all right. It's not that difficult. Okay, let me point it out. That one times this angle, correct? That moment is clockwise. The angle is anti-clockwise minus. Okay. That's 60. Rather than separate that side and that side and that side, I will just use the whole area there instead. Okay. Using one magnitude times that area minus that area. Well, that area and that 3 areas combined, 4 areas combined. Okay. That area will come to that term. That height is theta 1 times 2. Correct? Therefore, it's a half times 2 theta 1 times 2. That one. The displacement is up, force is down, negative. The second one, I will talk about this triangle here. There. That one is theta 2. That height is theta 2 times 1. Right? So, the area is that. That area will be calculated here. This height here is theta 2 times 2. The base is 2. So come to that. And that one come to here. That height 1.5 times theta 2. And then the rest is to 2 shears. That height still 2 theta 2. Like last time. That height 1.5 theta 2. You can separate into different case of forces, or you can change the name or whatever. Your calculation, your equation will rely on how you set up all those unknown displacement or angle. Okay? Then we still have theta 1, we have theta 2. So we have to link them. The linkage is here with that height. Oh, I just regroup them first, sorry. That height, okay, is equal to theta 1 times 2. Right? And also equal to theta 2 times 1. It's the same height. So 2 theta 1 equal to 1 theta 2. There. 2 theta 1 equal to 2 theta 2. 1 theta 2 equal to 2 theta 1. Sorry, sometimes I think too fast. Theta 2, right? Theta 1. Correct? 2 here. 1 here. Okay? Let's say that h is equal to 2 theta 1. Correct? That h is also equal to 1 theta 2. So that equal to that. Right? Therefore, we come up to there. Okay? So, move on. Then we change everything into theta 1. Yeah. Then take theta 1 out. Rearrange it. Oh, not yet. There. Into that. Then we said theta 1 is not 0. Inside the bracket must be 0. And therefore it works out shear equal to that value there. Positive. Therefore it means that what we assume is correct. There we are. Okay, so those are the 2 answers from 2 equations. And 2 drawings, of course. That's all. That's all for today. Any questions? No? Oh, it's so simple, isn't it? You understand everything? Well, I think when you try it, some question will come up. Okay, guys, 3:20. So, I see you guys after Songkran. Have a good journey and enjoy your project.